numbers. This section 2.1 is an intro to a lot of stuff that he's going to talk about in chapter 2. One key thing that he explores is what happens when you come across the square root of -1. It's odd. Why is it odd? It's odd because it's not real. It's called, you remember, it's an imaginary kind of thing. Well, imaginary means in our minds just the word that it does not exist. And really it doesn't exist. But mathematically and intuitively, what exists is the structure behind what it's trying to say. And what it's trying to say is that the square root of -1, even though it's imaginary, it is still saying something. That's the key that I want you to see. And I'm going to write something down. I'm going to show you. And it's going to be the secret behind these dang on imaginary numbers that if somebody had probably told us this, maybe in the 8th grade, oh my erkomai. That's the Greek deponent word, erkomai, to come or to go. Oh my erkomai. We would have been in a whole lot better shape now. Anyway, maybe my English there was probably bad, but but I'm going to show you this secret behind imaginary numbers. What are they actually saying? If you get that, everything else is easy peasy. And my thing is, if we don't get what they're saying, then doing that algebra, I mean, why do it? You know, what's the point? You know, why am I doing this? I want to show you that just with a simple example, and then I think, oh man, you're going to give me a hug after this. Well, maybe not. So, complex numbers, just a little something funny I thought from the book. Who is this kid warning us about our eyeballs turning black if we attempt to find the square root of -9? Let's look at this. The kid who learned about math on the street. And I'll tell you what, that may be pretty good to learn about math on the street. There's some people that got some stories. I know back in the 80s, and man, just talking when I was out ministering on the street, talking to some of these guys who were selling drugs and whatever, man, you wouldn't believe in terms of how they could deal with fractions and how they could add up these numbers based on whatever they were trying to sell. And I'm like, you know what? Y'all are pretty dang on smart. Maybe you ought to come to school and get a degree, you know, and not do what you're doing out here on the street, man. I mean, because they could like add and multiply numbers and fractions in their head that I'm grabbing my calculator, right? So if you divide 6,973 by 0, you die. Maybe some truth to that. No. Once this guy tried to find the square root of -9 and his eyeballs turned black. This girl, my brother knows, found out exactly what pi equals, but she went nuts. Well, I tell you what, math jokes are pretty lame, right? So this imaginary unit I, the imaginary unit I is defined as the square root of -1. And then if we square I, we square the square root of -1, and so we get I squared is equal to -1, right? Square this, we square that. So it's just I squared, and then we get just the -1. Complex numbers are defined as a plus bi, where the a and the b are said to be the real parts, and then the I, or the b times the I, is said to be the imaginary part. They're going to ask you to write numbers as a complex number in standard form. All they're going to be asking is to write the terms in this form right here. Okay? We're going to write it like that. And that's going to mean something in just a minute. equality of complex numbers, if I have one side over here, and if I have another side over there, if they're said to be equal, it means that the corresponding parts are equal. So the if and only if means that, look, the left implies the right implies the left. So here, if this is equal, that equal sign there, that means that the A has to be the C, that's what they're saying here, and the B has to be the same thing as D. That's all they're saying. Now let me give you the insight to what's really happening. Okay, and you will see this as the chapter progresses, but I think it's probably best that you see it now. And I think this is the proper way of teaching the mathematics. That is, for whatever reason, the philosophy of education for math for the last couple hundred years has been to separate algebra from geometry. But to do that does harm. That's almost like saying, okay, here is Benjamin, but we're not going to talk about Benjamin's as his body and what we see. We're only going to talk about what's in his mind. Okay. Well, what's in his mind you can't see, right? What's in his mind may be his thoughts, good or bad, whatever. So, but when I talk about Benjamin or Jamaria, I want to talk about the whole person. Do you see what I'm saying? I'm going to talk about who I see, what I see, but also what's on their mind, what's on their heart. So what math does, math has separated this idea of what I see, that's the geometry, with respect to what's in the mind or the abstract, that's the algebra. You see the difference there? The both ought to go together. If I'm going to deal with math, if math is supposed to be expressing what we see, if it's a building, if we're measuring the length or the area or the volume, I want to be able to see it first. And then let me put calculations to it. So my calculations make sense. So what I'm doing with X's and Y's pertain to something that we see. So here in algebra, the danger is we keep looking at paper with X's, Y's, and Z's, and you're like, what the heck is this stuff saying? You know? I'm not going to use this. Well, I'm not. Nobody will if it's just on paper with X's and Y's and Z's. But what does it mean? Let's start there first. So I want to show you that. So here's this example. What if you have f of x is equal to x squared minus 9. Okay. Just take that example right there. Now you remember that's a parabola and it shifts down 9 units, right? We got that part from back in chapter 1. There's a vertical shift down. What about those 2 points here? These 2 points there we will call x-intercepts. Now this negative 9 is the y-intercept. So I have x-intercepts where the graph crosses the x-axis at 2 points because I can see it from the graph. Now if we find those 2 points, what we do to find the x-intercepts, we set y equal to 0. Well, y is the same thing as f of x. We have y is equal to x squared minus 9. So to find the x-intercepts, we set y equal to 0. This is the symbol for and solve for x. So we have x squared minus 9 is equal to 0. That's no problem. We factor, right? This is x minus 3 times x plus 3 is equal to 0. So we get x equal to 3 and x equal to negative 3. So this is x equal to negative 3. This is x equal to 3. Those are the x-intercepts, right? Okay. So now consider f of, let's call it g. Consider g of x is equal to x squared plus 9. So instead of a minus 9, I put a plus 9 there. Consider x squared plus 9. So here's this graph. Now that's the regular parabola, you know, the cup shape, but we shift up, vertical shift up 9, right? So I go up to 9, 9. Okay. So that's the y-intercept there, 9. That's called the y-intercept there for this problem. Now the question here is, does g of x, which equals to x squared plus 9, does this have any x intercepts? That's the question. Does it? Does g of x have any x-intercepts? No. Look at the graph. X-intercept means where the graph crosses the x-axis. Here's the x-axis, here's the graph. Does this graph cross the x-axis? No. So there's no x-intercept. Look, x-intercept. Look, you just saw the Super Bowl, right? And the interception, oh, they did their interception, and I was just so nervous because I wanted the Rams to win. And then Matthew Stafford threw an interception. It just hurt my heart. But anyway, we won. But anyway, interception, right? Here, the graph intercepts with the x-axis. Boom, at that point. At that point. It's visible, I can see it. It's a graph. And so this graph now tells me that I can find numbers, algebra, that represent these 2 points. Right here. See how the algebra and the geometry go together? And when I see that, it makes sense. Now watch this. You come down here to this g of x, and here's the graph. Here's the xy axis. Then the question now is, does g of x have x-intercepts? This graph does not cross the x-axis. So the answer is no. So now we argue mathematically the reason why is no. Algebraically. We see it graphically, but why is that algebraically? Watch this. So I still do the same argument. We said x squared plus 9 is equal to 0. X squared is equal to negative 9. Take the square root of x squared. That's equal to, if it's x squared, it could be plus or minus, so that's how we get this plus or minus idea. Think about it. If something is squared, the result is positive, but you don't know if what was squared was negative or positive. Take the number, let's say, x squared equal to 16. That can come from 4, right? 4 squared is 16. But it could also come from negative 4. Negative 4 squared is also 16. So you have the possibility of plus or minus of the square root of negative 9. Well, they just said that the square root of negative 1 is equal to I. So this is plus or minus the square root of, this is 9 times negative 1. So this is plus or minus the square root of 9 times the square root of negative 1. I'm just breaking it down. So this is plus or minus 3 times I. Is plus or minus 3I on the graph? No, it's not. You know why? Because I is imaginary. It does not exist in the real world. So the explanation, the reason why g of x equal to x squared plus 9 does not have any x-intercepts, because here the roots are imaginary. Plus or minus 3I. That's why algebraically this graph G does not cross the x-axis. See, the algebra and the geometry must be linked together in order for it to make sense. Now look, folks, that's the end result of what this chapter is trying to get you to see. So they're going to play around with all these imaginary numbers throughout this section, but this is the end result. So the goal is, I don't mind doing the steps if I know where I'm going. If I'm just, it's a problem. What number? What's the formula? Is just plug this in, and what you got? I don't know, but I think that's the answer. Well, what good is all that? If I don't know what I'm doing, my thing is don't do it. If you don't know what you're doing, ask questions until you know. So, does this make sense?
I remember seeing this. I think that was like my sophomore, junior year.
Okay, my question, does this make sense? All right? The conjugate of complex numbers, you run into all these various scenarios. So the complex conjugate of the number a plus bi is a minus bi. And the complex conjugate of a minus bi is a plus bi. Folks, this is just terminology. So if they ask for the complex conjugate, then you know that you're talking about two things. This a plus bi and also this a minus bi. The goal is, why do you want the complex conjugate? Is because when I take a term and I multiply it, if I take this term here and multiply it by its complex conjugate, we get rid of I. That's the goal. No more I. That has theological implications, because it's typically the I that's getting me into trouble. The I is getting me into debt. The I is, okay, anyway. Oh boy, I wish I had somebody. So when you see this a plus bi has an I in it. A minus bi has an I in it, but when you multiply, it's just a squared plus b squared, right? You multiply, use the FOIL method. And so that's going to be the goal, where if we need to simplify to be able to write a term into the form a plus bi, typically we're going to use this complex conjugate. And we'll look at that when we get to it. All right. You know that problem that I was just showing you with the x squared plus 9 equal to 0, and we ended up with x squared equal to negative 9, and then I said that this was the square root of x squared plus or minus the square root of negative 9. Well, they're just saying here this is what we do with the negative in the radical, right? That negative 9 is negative 1 times 9. This is negative 1, right, times 9. And you remember that the square root of x times y is the same thing as the square root of x times the square root of y. So this is the square root of negative 1 times the square root of 9. So the square root of negative 1 is that I. And then the square root of 9 is just 3. You can write that as 3i, right? Because a times b is the same thing as b times a. So again, what these sections mostly do is just to show us the terminology. What does this mean? So if you see this in a problem, you go back and look at, okay, if they talk about conjugate, what is that? If I have a problem and I'm trying to simplify this square root of -4, then they're telling me that this is to be I times the square root of 4, and that's just 2i. That's what this is saying. So we want to make sure that we get what they're saying. What does that mean? Look, the information that's in the section that comes before the problems is 85% more important than the problems. I have to spend time with that information. If I have a section that I need to read to work problems, I need to look at that section and read. Do I read in math? Yes, I do. You're just sitting there working problems, you ain't getting nothing. You don't get math by just going to the section to work problems. You got to read. Got to read, got to read, got to read. And then you ask the questions. What is this? And the cool thing about the ebook in my math lab is it has various sections as you're reading that you can actually click on. And it takes you right back to like a definition or an example or something like that. That's really cool. So you use the information that you have, friends. The quadratic equation here, we can solve for x, and we got to pay close attention to the square root of -1, because that'll pop up, right? And so you remember the formula to solve for x. All we need is a, b, and c, and then we can use the formula to get the value for x. Well, let's look at some problems. All right, so the first is write the expression in standard form. What's the standard form they're telling us? The standard form is a plus bi. I want to write it in that form. So here, we're going to simplify. So since it's a plus sign, I can just drop the parentheses without any harm or any change. And then I'm going to regroup, put the terms, the like terms together. 1 plus 9. And then this is in minus 3i plus 8i. So 1 plus 9 is 10. And then minus 3i plus 8i is plus 5i. See how that looks like a plus bi? Another thing for that standard form is that look at where I is. That imaginary unit is in the numerator. So we're going to have some problems where the I is in the denominator. And they're going to say write in standard form, and that's when we're going to use that complex conjugate. So this one was easy, but here's the thing, folks. Take serious the easy problems, because they're the building blocks. Okay, so I can drop the parentheses on that 7 plus 4i. Well, there's a negative in front of the parentheses for 9 minus 4i, so I'm going to change the sign of everything in the parentheses for 9 minus 4i. So this becomes minus 9 plus 4i. See that? So that minus is multiplied to the 9, and then that minus is distributed to this minus 4i. So then I get the like terms together. If you see it, just go ahead and just write it. 7 minus 9, you see that? That's negative 2, right? And then the 4i plus 4i is plus 8i. So you got to be careful, because if you didn't notice these two negatives on that 4i, you would have had minus 4i, and your 4i's would have canceled, but that's not correct. This is the distributive property. A times B plus C is A times B plus A times C. What did we distribute? A negative 1. Right? Okay. Doesn't matter how they add to. Doesn't matter. We're going to simplify. We're going to drop the parentheses. If there's a negative in front of the parentheses, distribute that negative through. So this is 8 plus 5, minus 7i plus 6 plus I. So then I get the like terms together. The like terms means just the numbers without I. Get them together. That's an 8 plus a 5 plus a 6. And then get the i's together, minus 7i plus I. All right. So this is 8 plus 5 plus 6. That's 19. And then minus 7i plus 1i is minus 6i. All right. Okay. This is multiplying. When they say find the product, product means to multiply. And write the result in standard form. So product means to multiply, right? We multiply two binomials. We say we use the FOIL method, first time the first. So we have the first time the first. That's negative 1 times 1. That's negative 1. Then so that's the first times the first. Then the outer times the outer. Right? So that's negative I. Inner times the inner. 7i times 1 is plus 7i. And then the last time the last. So that's 7i times I. That's plus 7i squared. What is I squared equal to? Negative 1. Oh, you're so good. I love it. Oh, boy, you all are making me so happy. Boy, that's what I want to hear. Talk to me like that. That's right. So negative 1. Now, I'm going to go ahead. I'm just reading from left to right. So negative 1 plus 7i is plus 6i. This is plus 7 times negative 1. And then this is, now that 7 times negative 1 is just negative 7. So this is negative 1 minus 7 plus 6i. Well, this is just negative 8 plus 6i. Is everybody with me there? Adding two negatives, you add the two numbers and keep the common sign, right? The common sign is negative. So you add the two numbers, 1 plus 7 is 8. And then, since they're both negative, it's negative 8. When we add, you remember, let's go back. When you add two numbers with different signs, right here, adding two numbers with different signs, we subtract. So 7 minus 1 is 6. But the number that had the largest absolute value, without the sign, the biggest number, you take its sign and you put to the result. So 6 minus 1 is 7 minus 1 is 6, but 7 is bigger than 1. This is a 1 there. So, but 7 has the negative, so you attach the negative to the 6, right? Just my country way of doing that. Different signs, subtract the number with the largest absolute value, take its sign, put to the answer. All right, again, that's the same type. Multiply two numbers, multiply two binomials, use the FOIL method. Once you go ahead and do that, let's see what you get. Okay, so you got the first time the first, so did you get negative 20 for that? Okay, and then the outer times the outer, minus 24i. The inner times the inner, plus 15i. Last time the last, plus 18i squared. Yes, ma'am. And then this is negative 20 minus 9i. Okay, plus 18 times negative 1. Yes, negative 38 minus 9i. Is everybody good there? Okay, good. And again, get into my math lab, and when you start working the problems, if you get it wrong, it'll tell you, and then it lets you go back and try it again. It even gives you examples, of that, and it can show you some of the help that you may need. So use that to your advantage. When it looks like this, they're saying the same thing. You just write that out. So this is 4 plus 5i times 4 plus 5i, and then you FOIL, right? So the time is going to get me. There's two problems that I definitely want to cover, and then I want to try to give you one to do. So let me try to rush to those two to just kind of finish this up, and then when you come back on Thursday, we'll meet in room 103. They have computers at the desk, and then I'll let you get in there and you can look directly at these problems online. Okay. So divide and express the result in standard form. The standard form, remember, is a plus bi. This guy is not in standard form because the I is in the denominator. See that? The I is downstairs. We need the I upstairs. Because in the standard form, this is b times I. The I is in the numerator. So what we do is, if we have a fraction like this, and if we have the imaginary unit in our denominator, and it's a binomial, bi means 2, then I'm going to multiply to the numerator and denominator by the complex conjugate of my denominator. Remember, the complex conjugate helps to get rid of I. So the complex conjugate, if it's a plus bi, is a minus bi. If it's a minus bi, then it's a plus bi. So I'm going to multiply here 9 plus I all over 9 plus I. So remember, the numerator, you're multiplying just a monomial times a binomial, just to illustrate that. That's 7 times the 9. What is that, 63? And then this is 7 times I. That's plus 7i. Downstairs is the FOIL, but remember, it's special because all you get is just the first squared plus the second squared. But let's just work it out. First time the first is 81. Outer times the outer is plus 9i. Inner times the inner is minus 9i. Last time the last is minus I squared. So this is 63 plus 7i. Now those inside terms always cancels, and that's the whole reason for multiplying by the complex conjugate. He's supposed to go out. So all I have left is 81. That minus I squared just becomes minus 1 times the negative 1. That just becomes plus 1. But let me just write that all out. So this is 81 minus, here this is the I squared. You remember it was defined, I squared is defined as negative 1. So this is minus a negative 1. And if you get it, you can just always remember that a plus bi times a minus bi is equal to a squared plus b squared. Well, you say, what's b? Well, b would be 1. And then the a would be 9. So that would just be 81 plus 1 for our denominator. So this is 63 plus 7i all over That's 81 plus 1. That's just 82 downstairs. But they want us to write it fully like this. So you're going to say this is 62 over 82 plus 7 over 82 times I. And that's how you put it in my math lab. Now that 62 over 82 can probably be simplified too, right? So you got what 2 goes, what is that?
Is it 63 or 62?
63. Thank you. Well, it can't be simplified. We'll leave it like it is. Yes, ma'am.
In the math lab, it teaches the problem like that different, way different. So like
When you say the math lab, you say on the computer or at the Star Center?
like on the computer.
Okay.
It teaches way different. So like instead of like doing all that extra math, it's simplified by like you see like on the denominator how you have 9 minus I and you have 9 plus I.
Mhm.
What it do is it takes 9 and it squares it, and it takes I and turn it into a 1 and it squares it just to make it simple.
It doesn't turn the I into the 1. It's looking at the coefficient of I, which is 1. It's using this right here. That's what I just said. So here, A is 9 and B is 1. So A squared would be 9 squared, which is 81, plus 1 squared. So that's 81 plus 1, that's 82. I'm just showing you exactly what's going on, but here's the thing. If you get it, then you can just do that shortcut and just get your answer, and I'm fine with that, okay? But no, I is not 1. It's the coefficient of I that they're treating as the 1, okay? Yep, very good. Thank you, Jamari. I'm glad you noticed that. That is beautiful. That problem is a very similar type. That one is very similar. Let's do this one quickly. The one that I was trying to get to is an actual algebraic problem. Here they want us to simplify this. Now the square root of negative 25, I know if it was just the square root of 25, that's just 5. The square root of negative 1 is I. So wouldn't that just be 5I? And this is minus, wouldn't that just be 4I? And so all I have left is just I. Right? Is everybody fine with that? Does that make sense? Okay. Again, that works just like the previous problem. Let me just write this one step and then you can finish it. You're going to FOIL this plus this guy times negative 3 plus. Now look at that as being this. This is negative 3 plus 3I times negative 3 plus 3I. And then work it out from there. And it's a whole lot easier. So a lot of it is just simplifying. You know, before I can actually get to my final result, just simplify it first. That one works just like this one here. Okay, solve here using the quadratic formula. So I end with this one. So what you want to remember is if we have a x squared plus b squared plus c equal to 0, then x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And I forgot to tell y'all, like on the previous test, just remind me, if you forget a formula, just ask me and I'll write it on the board or something. Our goal here is not to test you on how many formulas you remembered. I'm just testing you on, can you use the information to actually work the problem? Okay. So look at this problem. A is 1. That's the coefficient of x squared, right? B is negative 8. C is 41. I'm just going to use the formula. So here we have x is equal to negative times negative 8. And just be careful with those negatives, right? Plus or minus the square root of here, b, which is negative 8, all to be squared, just using the formula, minus 4 times A is 1, times C is 41, all over 2 times 1. So x is 8 plus or minus, this is 64 minus, what is that? Is that 164? All over 2. And this is x is equal to 8 plus or minus the square root of, looks like negative 100, right? Make sure we don't throw away negatives. This is 8 plus or minus, the square root of 100 is 10, right? And the square root of negative 1 is just I, so isn't that just 10I all over 2? So this is x is equal to the 8 over 2 plus or minus the 10 over 2I. Simplify that. This is x is equal to 5 plus or minus, 4. I'm looking at the next one. 4 plus or minus 5I. Now, in my math lab, it'll ask you to put them separate. So you'll say, 4 plus 5I, I think comma, then 4 minus 5I. Okay. Well, just try your hands at that when you come in on, what I'll do is between today and tomorrow, I'll go ahead and just make a video for the next section and post that in course content. And then you all come on the next class day and just meet me in room 103, and they have computers there at the desk, and then I'll let you get in there and just start working problems, and if you have questions there, you can just stop me and we can look at whatever your question may be, and hopefully maybe this will be a better method for you to really get this stuff. Don't forget, next week Tuesday after class, retake on test 1, and then next week Thursday after class, retake on test number 2. And I think that'll do it. Thank you. Y'all have a good day.